So the first thing we did on Friday, the 17th, was after these notes were taken, should have been on Thursday, we went to the homework and did number 5 together. We're finding the open intervals where a graph is concave up, which means it opens like a cup, which means that its second derivative is positive, or it also means that f prime is increasing. Concave down like a frown, which means the second derivative is negative, or we could also say f prime is decreasing. We were to find any points of inflection. Those are places where the second derivative changes signs. And then we were backing it up with a graph when we were done. So we went and did number 5 together first, just because it's a tricky one. And then they were put in groups to work on 1 through 4. And then we finished the notes on 5.7, and 1 through 14 on this skill builder is sort of the Thursday, Friday assignment. So most left class with 1 through 5 done and number 9 done. So anyway, so let's go take a look at this graph. We're trying to figure out the intervals where the function is concave up with an exclamation point, or explanation, concave down, and explain our reasoning, and any points of inflection and explain our reasoning. We'll back it up with a graph when we're done. So the first thing we need to do is take a first derivative, which just comes nicely from our power rule, where we bring that power out front, we knock it down 1, and then we bring the power out front, we knock it down 1, disguised as denominator over denominator, so that'd be 4x to the negative 2/3. And then, because we're working with concavity, we're going to go launch into our second derivative. We'll bring the power out front, we'll knock it down 1. We'll bring the power out front, and we'll knock it down 1, disguised as 3/3. Which would give me 8/9 x to the negative 5/3. And I chose this one because this is where my work will differ from the key. We do need to figure out where that second derivative is equal to 0. But on the key, they factor it. And it's kind of hard to factor with these negative exponents. So I'm going to do it a little differently. I'm going to make this the cubed root of x squared in the denominator. That's what x to the negative 2/3 is. And likewise, I'm going to make this a 9x to the cubed root of, 9 times the cubed root of x to the 5th. And whenever we want to determine where a derivative or second derivative equals 0 or doesn't exist, we have to analyze the numerator and the denominator, which means we need a single fraction. Now you might be tempted to do the crisscross applesauce, which is fine, but you're going to end up with kind of a mess that you need to simplify. When we have like maybe 1/5 plus 3/13, it would be 13 plus 15 over 45. But when we have, let's say, 1/6 plus 5/12, we don't really need to use a common denominator of 72 when all this one needs is a 2. So you'll notice since these both have a 9, I don't need to multiply across to get an 81. So what I want to do is figure out what my common denominator is. So I'm going to take this guy, and I'm going to rewrite it as the cubed root of x cubed times x squared. That's pretty common when we have that numerator exceeding the denominator. We can pull actually a full x out of there. So when I do a rewrite on that one, I'm really looking for 4 over 9 times the cubed root of x squared minus 8 over 9 times x times the cubed root of x squared. And you'll notice we almost have a common denominator. We have the 9, we have the 9, We have the cubed root of x squared and the cubed root of x squared. The only thing we need to do is introduce an x on this one. So it's a little easier, I think, just to get a common denominator. And again, our single fraction then would be 4x minus 8. I like to factor because I know I'm going to be finding zeros. And on the bottom, we have 9x times the cubed root of x squared. This has two possible inflection values. Sometimes I call them PIVs. They are x equals 2, and that's where the second derivative equals 0. I'm going to go make a number line. I'm going to go put 2 on it. I'm going to put a 0 above it and an f double prime. We also, though, have a 0 in the denominator. And so that's where the second derivative is undefined. The original function was fine at x equals 0. It's the second derivative that's undefined. You have to watch out for that, though, because if the original function had had an asymptote, like maybe it had been x to the 4/3 plus 4x to all over x, you're like, oh, there's an asymptote at 0. Then when this pops out down here, I would suggest you put an infinity symbol above that so you know that there's no point there, that there's an asymptote there. That's going to happen with your number 2. Functions can and often do change concavity, concave up like a cup, concave down like a frown, at an asymptote. So we would have second derivative greater than 0, second derivative less than 0, but this can't be an inflection point. It's an asymptote. So we just have to be a little bit careful. Our 0, though, didn't cause a problem in the original function. So what that means when the problem's in the derivative is that we either have a cusp there, and we can change from concave up to concave down at a cusp, or vice versa, or we have a vertical tangent. Turns out it's this one, but you don't really know that until you go graph. All right, but we do know that we do have a possible inflection value there. So then you need to test in this function, the second derivative, these intervals right here. Well, x squared is positive for all x, so that's not going to affect the signage. So I'm really only going to look at the other two parts of that quotient, and I think I'll put in a -1 first. And when I put in a -1 for x, I'll get a negative on the top and a negative on the bottom for a positive. That means my function was concave up from -infinity, because there's no domain restrictions on our function itself. So -infinity to 0. And then, sorry, my phone rang, so I think I was testing a 1 in the function now, because I'm between 0 and 2, and that's going to give me a negative on the top but a positive on the bottom. So we're concave down from 0 to 2. And then if I put a positive, let's say 5 or 10 in it, it's going to be positive over positive. So I'm also concave up from 2 on out to infinity. Now it did say to explain, so this is because f double prime, our second derivative, is positive. This one's because f double prime, our second derivative, is negative. My points of inflection are at 0, 0 is not an asymptote. It's an actual point on the graph at 0, 0. And then also at 2. So you would say at x equals 0 and 2 because you can't use the word it, we don't use pronouns. It's because f double prime, it's not because it equals 0, it's because f double prime changes sign. Or the function f changes from concave up to concave down, or vice versa. The graph of that ended up looking like the function was increasing. How did it look again? Is concave up and then concave down, and then there's another small change in concavity over here at 2 and here at 0. So it kind of looked like that when we graphed it in my other class, or in class. So this is a little confusing here, but it is shedding water slightly and holding water slightly. So there isn't curved depravity, It is curving, and then we had a vertical tangent here, but notice we did change from concave up like a cup or holding water to concave down like a frown, likewise there as well. Okay. So and that's it. That was number 5. So then what they did is they worked together in groups on numbers 1 through 4. When they were done, we went and took notes on 5.7. We then went back and did number 9 in our groups. So they left here with 1 through 5 and 9, and a couple of them got a little farther done, but the assignment's 1 through 14. Hope to see you Monday.